Hi Lou, just bringing you up to date on what I'm doing with the proof of the fundamental theorem of arithmetic. Um, this is every positive integer greater than 1 can be written uniquely as the product of primes. So we start with, this is not really a proof, it's gathering all the different things together that have to be organized eventually into a proof. I haven't gotten all the way. But let's look at colors, 6 colors put into columns 8 high. And you might notice we don't have any numbers on these. This is just purely colors, blue, yellow, green, orange, purple, red. Now I find that when you put the numbers on, people don't really look at the colors in the patterns. They get fixated on the symbols. So this first part is just colors. So if you notice, the colors break into 2 different parts with this setup, where you have yellow, orange, red rows. Now the rows are slightly off; they're not lined up, but the color scheme is always the same. And if you look at the other rows, then you've got the purple, blue, and green all together. If we look, every third ball in a row is the same color. So you have yellow, skip 2 rows, the third row is, or the third column is another yellow. And that works on all the columns. Now there are most 2 rectangles. This has to be worked with, because if you only have six colors with four high in the columns, then you're not going to have a rectangle, obviously. But if the number of colors is less than the height of the rows, then you get this rectangle, the vertical rectangle, which defines the pattern. Putting blue, yellow, green, orange, purple, red, and then repeating. But that, if the height of the column isn't high enough, then you're not going to get a rectangle. So notice they're the same all over the place because of the way we've set this up. But if we look, we can find on any one of these, we're going to have a rectangle with all 6 colors. Here's a 2 by 3 or 3 by 2, depending on how you look at it. And no matter where you put this rectangle, you're going to get 6 different colors. And those are the only 2 rectangles you can do that in this picture, though the vertical one might not always occur. So we can extend this thing, which is just mind-blowing. I mean, how can you take all that in? But if we start looking at just the regular colors of this color pattern that's been extended to the entire plane, you get certain things that are fairly obvious. So here's just the blue, and look, there's a nice lattice, parallelograms. But if we look at the ones right above it, the way we've set this up, that's the same pattern. It's just been translated. And the translations, you can translate to the left, to the right. If you put one ball, just through translation, if you put one of those yellow balls on any of the other yellow balls, it matches totally. And so here's green, here's orange, here's purple, and here's red. Now what's interesting is that each color defines a lattice on the plane, and these are all congruent and disjoint from all the other color lattices, and the union of this totally fills the plane. So we've broken it into disjoint congruent sets. Now, if we number the balls as they fall, then our attention is pushed to something else. So here it's the same 6 colors, but now we've numbered them as they go in. And you're automatically drawn to the numbers rather than the colors. The symbols just overwhelm the colors. But we can get various things out of this. Say we do two columns or 8 columns, then if you notice, the color pattern is the same. The numbers are different, but the color pattern is the same. So here we go. You can see that 1, 2, and all the way to 1, 8. 8 columns, 2 columns, same with 14. Every time you add 6 to it, you get the same color pattern. And if you extend it out to the entire plane and ignore the numbers, you get the same pattern. So the color patterns are the same if the 2 different heights of the columns are congruent. Mod the number of colors. Now, going back to just 8 columns, 6 colors, since we're doing this with the column height of 8, then that means that the numbers across the top column, are the multiples of 8. You've seen this before. I threw in the 0 on this one just so that we could do it the congruent modulo, because you want 0 through 7, not 1 through 8. So here's, let's see, the numbers congruent to 0 mod 8, congruent to 7 mod 8, 6, 5, 4, 3, 2, 1. So each row are basically numbers that are congruent to the smallest positive number in the row, or to 0. If we look at all the red balls, then these are all the multiples of 6, which are the number of colors. And if we had 7 colors, then it would be multiples of 7. And if we look at the purples, then they're not multiples of 5, but these are all the numbers that are congruent to 5 mod the number of colors. So this is 29 is congruent to 5 mod 6. 77 is congruent to 5 mod 6. So these give you all the numbers that are congruent. And if you extended it to the entire plane, then you'd get all of these many times over. Okay, now the smallest numbered ball, which is on the top row and has the color of the ball with the number of colors, is the least common multiple of the number of colors and the height of the columns. Very complicated, but basically what it says is, hey, the red balls are multiples of 6, the top row are multiples of 8, so the smallest positive number on the top row is the least common multiple. Trying to say what it is makes it more complicated than what it really is. Now, what we notice is that since we're putting these balls in, the colors, just, blue, yellow, green, orange, purple, red, and then repeating blue, yellow, green, orange, purple, red, what we're going to do, if we go over 3 columns, 24, then we're going to have to put in three times these colors, and we'll end up with 48. Now, we keep putting in the same colors in the same way, so we better get the same color 3 columns over. And we saw that with the colors. But if we look at the numbers, what this turns out to be these, if we extended it out just in a band, not over the entire plane, this would be all the multiples of the least common multiple of the number of colors and the height of the columns. Now, if we look at the top row, these are all the multiples of 8. We look at the colors there and we pick the smallest number with that color. Turns out that this is the greatest common divisor for the number of colors and the height of the columns. And this can be shown through a modulus argument, which would take a little bit more effort and use a slightly different picture, but it's doable. Because any number that's divisible by 6, or is a divisor of 6 and 8, will divide any multiple of 6 plus any multiple of 8. And you saw with the paths on the other one that if we can get from that upper row down to 2, that's basically you're looking for whole number solutions of 6x or 6n plus 8m, or 6m plus 8n. So we're looking at whole number solutions, and so any number that divides 6 and 8 has to divide an integral, let's see, the sum of an integral number of 6's and an integral number of 8's, so it would have to divide 2. And any whole positive number that divides 2 would have to be less than or equal to 2. So 2 being the smallest one you can get means that 2 is the greatest common divisor. Or, well, that anything that divides 6 and 8 would have to divide 2. You actually have to show that 2 would divide 6 and 8. Okay, here's another thing. Let's see. Product of the greatest common divisor and least common multiple. You take 2 and you look at 24, which is the least common multiple. It takes 2 of those rectangles to get to 48, which is the product of 6 and 8. Okay, here's extending the balls and the numbers out in terms of a kind of a band, so you don't get any numbers twice. So every whole number is in there just once. And then this extends it through the entire plane. Kind of overwhelming. Now here's 6 colors with heights 1, 2, 3, 4, 5, 6, 7, and 8 to give you the patterns that are developed. Now, the balls and numbers with circles around them are the greatest common divisor. And the ones with the squares around them are the least common multiple. And here's the rectangle that has all 6 balls in it. And I would call that the standard rectangle. Now notice, if you have only a horizontal with all 6 balls in it, every row has every color. But if you have, say, looking at 3 height, a height of 3, then you're going to have 3 different color rows. 4, you have 2 different color rows, but 2 is the greatest common divisor of those 2. So the greatest common divisor tells you how many rows you're going to have with different color bands of colors. Now look at 6. 6 high, 6 colors, pretty bland, but it's fairly important. You get rows of colors. And an interesting thing, if you go over, since there's 6 colors, if you go over to the 6th column, notice that the ball at the top is always going to be the color of this the sixth ball that goes in. It would be red. So 6, 12, 18, 24, 30, 36, 42, 48. But that's important because if you look, then the height of the column, well, if you have the 6th one is red, then that means that the only time you can have this pattern repeating where the 6th one is red would be where the top ball in the first column is red, second, third, all the divisors of 6. You're not going to have one with 4 or 5. And if you have something that's 5 high, then there's no way that you're going, the columns are 5 high, there's no way that you're going to get a red one in the 6th column. Now, here I've done 5 because it's prime, and that will have a great bearing on the fundamental theorem. Notice the standard rectangle in each one of these is either vertical, if the number of colors divides the height of the column, otherwise it's horizontal. Every row has every single color in it. And that's about as far as I've gotten. This is a jumble of different facts, and they really have to be put together kind of Euclid style to get a flow going where certain ones are shown first and then others follow from that. Hopefully this shows you some of the patterns. There are a lot more patterns in here that I haven't really shown or indicated a proof for. But this is what I'm working on now. This is actually, of all the pictures I've drawn, this proof is the one of which I'm the proudest because I think it has the most depth to it. Oh, and the 5th column, top of the 5th column is always purple ball, which is the color of the ball 5. And I haven't really gotten much farther. It takes a while to put all these stupid numbers in the different colors on these balls.